I would.
So I think we're ready to go then. So welcome to 10 to Dine, building possibility spaces with Neo4j. So before we get started, I want to set the scene for you, get a little bit of a mood going. So picture that you are at the wrought iron gate of a gigantic mansion at the top of a hill. And you're approaching a door and you have a mysterious invitation in hand. You don't know why you're there, but you're going to find out. And behind you, you see 10 black Cadillacs pulling up behind you, one by one. Different people get out. Everybody talks to each other. Nobody's quite sure what's going on, but they're gonna go have dinner together. And you know, 9 people come, one person dies, or 10 people come, one person dies, 9 people leave. So this is your classic whodunit. And it is a really fascinating use case for what we want to model and show you today, because it's a genre that everybody is familiar with. It's been done over and over and over, and yet the devil's in the details. Like, we still love the whodunit. It is still being written, produced, tons of content in this structure, because even though all of those hallmarks are the same, the details are so interesting and compelling, that keeps us going. So we've chosen this as our backdrop. Um, so for those of you who are tuned in, who may be exploring Graph or Neo4j and Graph databases for the first time, to just help you establish your footing, I'm going to give you, jumping the gun a little bit. Who are we?
Yes.
Who are we, Kelson? My name's Brandon Campbell, Kelson Smith. We live in Ogden, Utah. I'll speak for myself first. I am a strongly convicted graphstronaut. I love graph database, and I consider myself to be an evangelist. So if you need somebody to preach graph to you, you can get with me and we can have a conversation. I'm also a software engineer by day, dabbling game designer by night. So what you see on the screen right now are 2 projects I've worked on. The first one's called Omicroid. That was an alien bacteria simulator built to help kids learn how the scientific method works and use clay-mated sprites. The second is a project I'm on right now, the Glad Hollow Nasties. Glad Hollow Nasties is a dark German fairy tale survival royale where you play one of a troop of naughty kids avoiding a monster who's picking you off one by one. So the Glad Hollow Nasties in particular will be using some of the techniques I'm going to show you today, and we're really excited about both of those projects.
And as mentioned, my name is Kelson Smith. I'm a full stack developer. I view myself as a little bit of a maker. I collect all different kinds of hobbies, anything from woodworking to web design to recently blacksmithing. I just love anything that has to do with making things, and I'm a bit of a creative as well. And I really, really enjoy the kind of stories and things that we can design using some of the techniques we'll come to today.
So graph in a nutshell, getting back to where I was before. All graphs are built with a very simple structure that starts with a node. So a node can be anything. In this case, let's say the node is a person. And not just any person. We'll say that this node is a particular respected French woman. And let's forgive me in advance for butchering this pronunciation, but we have the reputable Charmille Leguin, who happens to be a detective. So what we have right here is your most basic graph. So if you're new to Neo4j, this is a structure you'll become really familiar with. 2 nodes and an edge connecting them, describing what the relationship is. So what's so beautiful about graph is you take this really basic structure and you can use it to model pretty much anything. And it's very elegant in that respect. So for example, we can add a little bit of detail here to Charmille. In this case, she is working on a case. which involves a murder most foul. So let's talk a little bit about what the use cases are for graph in the industry and how what we're going to talk about today differs a little bit from those use cases. So typically, or what we've done professionally and what we've seen in our graph exploits in our own personal time, is it's very common for industry applications to use graph to aggregate giant chunks of data, synthesize them into some usable form, and then output some answer. So the flow of that pipe goes from data to knowledge, with the output being some kind of knowledge graph very often. That is so valuable to the industry. I love it. The technologist in me is very invested in this pipeline. But in addition to being a technologist, I'm also a creative. Kelson can agree here. And so I wonder, as a creative, what can we do with graph to make something? Not just to analyze something or ingest something, but to create something. So what I really want to know is what happens if we turn around the pipe and we start with knowledge and we put out data. So you may be asking, why would you want to do that? Why would you want to generate data with a knowledge graph? And there are actually lots of good answers to that question, but let me recontextualize this for you in one simple way. Let's substitute data for content. So you're not outputting data, you're outputting content. Now, content is the lifeblood of the internet. It's the lifeblood of our culture. It's a big money industry, and it's really difficult to produce meaningful content procedurally. So our strategy that we want to communicate with you today is how to use Neo4j graph database to procedurally generate meaningful, semantically interesting content with juicy emotional experiences, how to generate story, something that has traditionally been extremely difficult using some other method.
And to give you guys a little bit of a background, if you aren't familiar with a lot of the techniques used for procedural generation.
They're saying very low volume.
Oh, sorry.
I apologize.
So a background on procedural generation. I need the mouse.
Yeah, sorry.
So a possibility space is all the possible outputs that a specific generator can give you. This term differs a little bit in uses, but this is the definition we're going to go for. So we have in our possibility space that is going to be a very simple platforming level, just to give us basic groundwork. We're going to have a rocket, which is our character. We're going to have some blocks that's the terrain we're going over, and a flag that's our goal. And our possibility space is everything that can be made with those three items. So here we have a little level. It's some blocks. We start on the left and are trying to move to the right. Not particularly interesting, but it's technically a game. If we just randomly place our objects, determining if each square in our grid could be one of those objects, we end up with something that looks a little bit like this. It's not useful. There's a bunch of rocket ships, a bunch of flags, trivially easy to play or impossible to play, depending on how the game is built. But either way, this isn't a good output. So we add some constraints. We make sure that there can only ever be one rocket and one flag. And we think ahead a little bit and make sure that there's always one rocket and one flag. We just encountered another problem. We can't actually get our rocket ship to the flag. It's blocked. Now this one kind of works if you go up and around, but if that's outside of our play space, then this would be an impossible level. Same with this one. So we need to add another constraint. We need to make sure that you can always finish the level. And as you're going, you're having to add more and more constraints, and you spend a lot of your time writing edge case if-else statements and things like that. Things that make it so you are cutting off parts of your possibility space to make sure that it's playable. This is just a lot of effort. And if you're doing this, you'll even encounter another problem where, as you're going to get a lot of very boring levels. And we get into the problem known as the 1,000 bowls of oatmeal. If you make 1,000 bowls of oatmeal by just throwing oats in a bowl, every one of them is going to be unique. All those grains will land in a different random way, but the experience of eating it is the same. Because there was no real design that went into it, it was just all randomly tossed in there. There's not any sense to it. So a common way to get around this in the procedural generation industry is to use a chunk-based or a modular methodology, where you hand author a bunch of small chunks, and here I've made a few, and then slot them together. And you can guarantee that the level will always be playable and at least somewhat interesting if you design good chunks. You'll end up cutting out a lot of the low lows of non-playable levels and super boring levels, but you'll also not have any of the high highs, super interesting ones that you couldn't have thought of anyway. All these levels, again, start looking a little bit samey because we haven't built enough chunks. We're back to the 1,000 identical bowls of oatmeal. Now imagine how difficult it would be if we add an extra star, an extra part to our game. In the pure random algorithm, that's not too bad, except that you're still having to add more and more edge case constraints, always guarantee there's a certain number of stars on the level, or that the stars are also reachable. So it gets a lot of programming time in that. And you end up spending a lot of time in level design if you're building a bunch more chunks that involve these stars. Just all these different levels out there. And we have to go and find the good ones. And there's actually quite a few good ones out there. But it's really hard to find them in all that noise in the background. And that's because our generator lacks context. It doesn't know what's interesting or what should relate. We can kind of hand jam it in there a little bit by adding checks with context, but that's a really inelegant solution. These generators don't know how the elements of the game are supposed to relate. And I just mentioned the word relate. We're at a graph context. We got all these little bubbles of interesting bits out there. I think we just made a graph.
So how are we doing on the volume? Are we still low? Okay, well, I'm not sure, so I apologize if you can't hear me, but we'll try to lean in close as we can. So our technique to generate content with a graph starts with an axiom. So axioms are a concept that we've borrowed from formal logic, and at its most basic root, it is what we're calling a self-evident truth. So an axiom is a piece of content that can be distilled down to an atomic level that is very small and easy to implement in a graph. So just as an example, if we were to create an axiom to start describing what we know about our murder mystery, we might say that 10 people go to a party. That's a very simple statement. There isn't any extra fluff involved. You've got the 10 people, you've got the party, and you've got an action. So that is our first axiom. Now, there are a ton more that we can add, but by building in this way, we can start in a very small and modular manner. So if we add another axiom, this is technically independent, right? One person is dead. That's another true fact about the possibility space we want to create for a murder mystery generator. Death could be accidental. It could be murder. The murder has a perpetrator. The perpetrator is going to have a motive. The perpetrator has an opportunity. They do not have an alibi, and they must have a motive. So in the classic whodunit, you know you found the killer when you found somebody who had opportunity, motive, and who has no alibi. So we're going to use those as our hallmarks, and they can be expressed here as axioms. So money might be another motive for murder, etc. So taking these axioms, we can build a graph. So here are our axioms listed just in a quick recap. To translate these into graph, we might do something like this. So our first axiom might be a person goes to a party. So there might be 10 people, which could be expressed as a property on this edge, or up to 10 people, and you can express probability distributions in this way to kind of control how many people. But the most basic axiom is like expressed thusly. That person or a person might experience death. That death could have been an accident or it could have been murder. If it was murder, there's a perpetrator. The perpetrator has a motive, an opportunity, no alibi, and they might be murdering for love or money. So here is the graph representation of our list of axioms. And the more axioms we add, the richer and more dynamic our graph becomes. And this is functionally a template. This is our possibility space. So anything that can be described by this scenario is a possible output for our generator. So in order to actually unfold this possibility space into an instance, we have a couple of grammars that we're applying. So I wanted to go over those briefly so you kind of know what exactly it is we're doing. The first is has. So in this case, we would say the mansion has a room. The room has a door. This is the most basic building block for your possibility space, and generally speaking, will be to build out your world. The next important grammar is the could be. So the could be is used for picking an option out of an array of possibilities, and there may be subgraphs that indicate whether or not that could be is applicable. But in this case, an example that I'll give you is, say, somebody's name. Their last name could be dependent on their nationality, or it could be dependent on, well, let's say their first name could be dependent on their gender, and maybe not, but you can model all of those things as could be's. And then our last most important grammar is the choose. So choose is used to select something that has already been generated by the generator. So for example, in your first pass, maybe we create a world, continents, countries, habitants, cities, roads. But in your second pass, you might want to pick some of the people that you generated and make them interact, do interesting things. That's where your choose grammar comes in.
All right. So with our possibility space, we're essentially able to describe a multiverse of, in this case, murder mysteries. And there are many different possible murder mysteries that could come out of it, especially if we construct our possibility space large enough and add enough things in there. We can get a huge amount of variety. But we need a actual output, an instance, a universe to be usable for something beyond just the possibility space. And so we have built a relatively simple algorithm. I think it's just over 200 lines now.
Yep.
That is able to traverse any arbitrary possibility space and use the grammar that we just defined. And there's a couple more smaller things in there, but a fairly simple grammar, go through and generate an arbitrary possibility or an arbitrary instance. We call it our multidimensional cookie cutter because we're stamping out a little universe for ourselves. So here we have a very simple possibility space. A mansion has a floor, has a room. These rooms could either be a bedroom or a library, and a room might have a character in it. We pick from one of the characters that we've generated elsewhere in our possibility space. So we start at the mansion, and our cookie cutter sees that, and generates a mansion node here on the right. We then go and generate a floor, and in fact, we have some extra logic sitting there on that relationship as a property that says, hey, there can be a number of floors. In this case, it generated 2 for us. And we are using depth-first traversal to help manage some of the dependency requirements here.
Say the butler chose to do it.
Almost certainly. So we have the first floor, and that has multiple rooms in it. We now need to figure out what those rooms are. And we have these 2 different could be possibilities. It could be either a bedroom or a library. those two, and we pick from those options. We pick 2 bedrooms in this case. So the first floor has 2 bedrooms on it. We then go back up the tree. We go to the second floor and see, all right, this one has 3 rooms. The second floor has 2 libraries and a bedroom. This is kind of a weird house. It's only libraries and bedrooms, but I'm not going to judge. And we have generated these. Now we go and we connect our rooms. Once the rooms have been generated, we connect them to a character. In this case, we've named our characters after some of the classic roles you'll see in something like Clue or the murder mysteries. So we have a flirt character. And the flirt, we find what remains of him or her inside of the bedroom.
So before we answer the question of why, I want to show you guys what our implementation actually looks like in Neo4j. So if you'll give me just a moment here to pull up our graph. This first graph I'll show you is our possibility space that we generated for this example. And there's a lot of stuff going on here. And if you've worked with graph, this is probably a familiar sight to you. If you're new, maybe this looks a little bit overwhelming, but let's jump into one specific element. So if you look right here, we've got a character node. I'm going to take a closer look at this one and talk a little bit about how we're modeling our character. So if we expand this node, we can see there are a bunch of possibilities associated here. So the character could have or must have a personality. They must have a name. They must have an intelligence level. They must have a gender. And there are these. The name must have first name and a last name. And the first name is determined by the gender. So in this way, we're expressing what the rules are, what can happen, what relationships are meaningful, so that you don't get a combination that doesn't make sense or that doesn't represent a meaningful output.
We were asked to zoom. I don't know if we can zoom in.
Oh, no, we can.
Yeah, okay.
We'll zoom in.
I think we're zoomed in all the way.
Yeah, looks like it. I should have styled the nodes to be larger for this.
You can go and just click down on there in the bottom and.
Oh yeah, let's do that. Well, that won't make the font bigger.
It'll make it at least easier to pick apart which ones are there.
If you're interested in some of this content after, we can send you maybe something a little bit easier to see. I apologize for the small size there.
Able to zoom inside of your desktop browser, right?
But yeah, I also wanted to expand the personality here really quickly.
Yeah.
Kind of see how we've modeled this. So the personality, we chose to use the Myers-Briggs personality model because it was easy to implement in Graph. So it has 16 personality types that are based on a combination of whether you're introverted or extroverted, whether you're sensing versus feeling, those kinds of things. And what's interesting about that is that the way those types of people interact is something that we can speculate.
Mm-hmm.
It's something that we can express in terms of an axiom and something that we can put in arbitrarily. So these two personalities might interact this way, they might interact that way, and we can express which one is the more likely of the two. And then the possibility space can generate a person that has a unique personality and another person with a unique personality and produce an interaction that's organic. And it's a very expressive way to model it. So we're getting long in the tooth, so we'll wrap things up really quickly by showing you guys the actual implementation. So that was the cookie cutter. This is the cookie. So we'll start with the mansion. It has a ground floor. It has a second floor and a basement that are connected by stairs. In the basement, we have a parlor. So the basement parlor, that's suspicious.
Yeah.
And in the basement parlor, we have 3 pieces of furniture and 2 characters. So let's take a look here at who we have lurking in the basement parlor. I'll scoot that over. All right. So on the right, we have a 35-year-old male reporter with the ENFJ giver personality type. So a feeling type, an extroverted feeler, by the name of Mickey Souza. Average intelligence. And then on the right, we have the old money aristocrat, female, 45 years old, so 10-year difference, named Harriet Noble.
A little bit on the nose there with the last name, but
so the question then becomes, what are these two doing together in that basement parlor? And we've got actions modeled in passes. So in our possibility space, we've modeled a step, which would maybe be some arbitrary amount of time.
could be an hour, could be a
Yeah.
minute, whatever.
Where the characters can interact. And each interaction results in an action, which are shown here. So we are going to be working a lot more on this for an expressive story to really emerge from it. You know, what you see here are the bones. But the more axioms we add, the more flesh we put on, the more contextually sensitive and relevant that the story we're generating becomes. So you can take a story, you can break it down into its the archetypes, the pacing, what are the critical plot points, a character arc, how do you model that? All of those things can be broken down into axioms. We can put them in a possibility space, and we can feed them through our 200-line generator. And it can take any of those and expand them into an instance. So let's jump back.
I'll grab the mouse again.
Yep.
The beautiful thing about this is that because the output is data and the inputs are data, you can kind of bring your own stack to this. You can use it for content creation for games and stories is the obvious one that we've thought of. But you could also be used for like modeling a possibility space for idea generation, or for data generation if you need to have a randomized but large complex object. You can use this same methodology.
Lean in a little
Yep.
closer.
You can use that same methodology for generating all sorts of different things. And we've kind of named our tool methodology HoloMorph. It comes from the Greek word for something that is simultaneously a whole and a part. Basically, the whole thing is described in the parts inside of the database. I got a little landing page over at holomorph.dev. If you're interested in following along with us, we'll keep you posted on what we're doing. I think we're considering open sourcing part of what we're working on. We're hoping to have an Electron-based React app to help generate these possibility spaces.
So HoloMorph will be a tool to build a possibility space if you're not a graph expert, and it'll be plugging directly into a Neo4j instance. And if you are a graph developer, you could bring your own possibility space and use HoloMorph to stamp out an instance. So yeah, if you're interested, please stay tuned for that.
All right. Well, thanks for letting us come and talk about what we've been working on. Is there any questions out there? Oh, and some pop quiz for you guys.
So I don't know if they introduced this in the keynote. We were getting all set up, but throughout the conference today, there are going to be questions at the end of each briefing. And if you get the most points answering those questions, I think there's something like a $50 swag reward from Neo4j. So if you know the answers to these questions, you can go submit them. And I think, so what about ReactJS? That is the HoloMorph project, and we definitely wanted to spend more time talking about it, but we will have to expound later just because of the time constraints to get the concept across. So apologies there. We're using Force D3 React component to visualize the graph. It's really cool, easy to use, and so yeah, we're plugging into Neo4j and building our Electron app in React.
Got the question: are you stating this generates every single possibility in the space?
Technically, no, right? Like we're targeting. It's that it could generate any possibility in the space. When you run the generator, it's going to output one possibility, but that possibility will fit within the constraints and the rules and the relationships defined in your cookie cutter. So if you wanted another, you just run it again. And I guess if you run it X number of times, theoretically, you might produce every possible outcome. But depending on how many axioms you put in there, that's going to be pretty difficult to do. Can you demo the React generator? I'm not really set up to do that yet, but we will be forthcoming demonstrations of it. Do we have any others?
Did we miss any earlier?
Let's scroll up here. I think we covered it. All right. Well, thank you guys for tuning in. Really appreciate your participation, and we'd love to hear from you and have ongoing.
Oh, another couple questions.
So we have two actually. Let me. It's holomorph.dev. Holomorph.dev. So we actually just put that up last night. There isn't a lot on there yet, but we will be fleshing it out. So bookmark it, whatever. We'll be.
There, you can drop your email in there, and we'll let you know when we have some more.
Right. And I also wanted to direct you to the Facebook page for the Glad Hollow Nasties, the project that I'll be using.
One more to the left, tab-wise.
Oh,
there you
go. So since I have just a minute, I think we've got till 8:40. Correct me if I'm wrong, Karen. But the Glad Hollow Nasties, we're going to be using HoloMorph to procedurally generate backstories for a host of unique naughty children. Really excited to see what we can get out of that. But the idea is that at a very regular basis, we'll be releasing new characters to go play in that survival royale, the Haunted Forest, to avoid the monster.
Yep. And it looks like if you're wanting to answer those questions, there is a link in the chat for the Hunger Game questions if you want to win some cool Neo4j things.
Oh, we got another question.
And timeline set of nodes or the timelines imposed by the cookie cutter. So the timelines are currently they're a set of nodes, although we've also been experimenting with because we generate a graph, it's perfectly possible to have the game in the end continue using the graph. So you can keep all of the data in the context that you have in the rich data set that is there. And so then you can later go and generate those nodes.
So yeah, I think our end game would be, or at least this is my idea. Sometimes Kelson and I disagree, but would be to create some kind of game where you're racing a detective to figure out who committed the murder. And that's really an information problem. So the game is essentially a graph traversal problem. So this works really nicely in that context where you'd be using a graph for your game model and then saving the game state as you're going, updating the graph, connecting the nodes that you know about, and essentially you'd be working your way through a maze to get to the end.
And if I could shout out a game, it doesn't use procedural generation, but Outer Wilds is a recent game about basically exploring a solar system at the end of the universe. And through that, all of the clues that you're finding are actually placed in a graph for you to go and trace down all the relationships and things like that. And that is an extremely fun game and a compelling mechanic. Anytime you've ever seen in those like the crime shows like a cork board with strings pulled between them. That's just a graph right there of people connecting all the clues. So what we're doing is generating the world that then a player would be able to go in and draw and put those strings and those pins in pictures and things like that. And again, the name of that game was Outer Wilds, not Outer Worlds. Outer Wilds. There's some name conflicts in that space, apparently. All right. Do we miss any other questions in there?
Well, I think that
All
brings
right.
us home. Yeah,
Yeah. Thanks again for joining us.
guess we'll probably hang out here until our session is over. So if you do have any questions, you can stare at our faces while we wait. Yeah, you're welcome. It was a pleasure to be involved in this conference. And we've had a lot of fun putting it together, and we hope to be able to do more in the future.
Spencer, do you have a question, or are you just raising your hands in joy? I guess high fives.
Thanks, Jason. Karen, you can probably see that comment from John Tinsdale. He says that the talk schedule is coming up blank for the rest of the day. I think that the buttons might not show up until the time or until it's open. Not sure about that.
Yeah.
Yeah, we will be up submitting to Graph Connect. So,
Oh, that's a good question, right? What is the best way to tease out axioms?
Yeah, I think that's really an art form.
Yeah, that's really where the creativity gets put into this.
Honestly, we're still figuring that out. Like we've revised the model 3 or 4 times. The nice thing is that it's super easy to start over. So you can scrap your possibility space and start over because it doesn't take long to build. You just have to, think about how you want to model it. And there are some considerations you have to make about the traversal order to make sure that certain instances have been stamped out when you need them. And we're hoping to improve that with better grammar.
A large part of the reason why we weren't ready to demo the actual or set up to demo the generator itself was just because the grammar is in a bit of a fiddly state right now, where we have to add a couple of extra dependency. Dependency, what is the term?
Sorry, I was reading the chat.
Okay. Dependency resolution. Yep. Dependency resolution is a pretty big problem with our current implementation, although we've got some ideas for how to resolve that. And yeah, but it is, once you get going describing some axioms, it really is something that you pick up pretty quickly once you just get in the sort of formal logic headspace of let's describe this thing. And the nice thing is it doesn't need to be technically true about the real world when you're describing
just what
it.
you want to happen.
Because it is not a universal truth on Earth that 10 people go to a party. But by saying that 10 people go to a party is a truth in our possibility space, we guarantee that is for our possibility space true.
Yep.
And you can always go in and add more granularity there. We could easily go in and say that between 7 and 13 people go to a party.
Which is really one of the reasons that the axiom-based possibility space in a graph is so good, because it can expand and grow so much more organically. Because when you want to add content, like in your example, if you've built your constraints in code, that can be a real challenge. But if your constraints are defined as a possibility graph, then it becomes much easier to integrate.
All right.
Well, I think that's time. So,
all right.
Thanks, guys.
Enjoy the other talks.
Yeah, we're going to go tune in ourselves. So as soon as I figure out how to close this.